In this lecture, we're going to exhibit the primal dual algorithm that solves the assignment problem and prove some things about it. But before we get down to the details, we'd like to take a very broad perspective about what are the ingredients of a primal dual algorithm that make it run. A primal dual algorithm consists of, first, a link between the primal and the dual. In addition, at all times, our primal dual algorithm is going to have some dual feasible solution in mind. From this dual feasible solution, it's going to use complementary slackness to make a primal solution. Occasionally, this primal solution that it's constructing is going to be a feasible primal solution, and in that case, we terminate the primal dual algorithm. But usually, the primal solution that it constructs is going to be infeasible. And when we have an infeasible primal solution, we go back and we somehow update our dual feasible solution. In the case of the assignment problem, our dual linkage is going to be an update to our weights. We have some edge weights, and we're going to update them by subtracting the weight of the edge I, weight of node I, and the weight of node j. Our updated weights are going to be called C bar. Dual feasibility in our case is going to mean that C bar is going to be less than or equal to 0. This implies that our constraint in our dual is going to be satisfied. The way we're going to use complementary slackness is for every tight constraint, that is for every C bar that's equal to 0, we're going to somehow use this edge ij. And in particular, we're going to use this edge ij by finding a matching among all the edges associated with tight constraints. In our case, we know that the primal solution is going to be feasible whenever the size of our matching is equal to n. When this is the case, we know that we can match every vertex in V1 with some vertex in V2. Infeasibility is the opposite, that is, the size of our matching is less than n. And in the case of infeasibility, we're going to update our duals u and v. An important feature of our primal dual algorithm, and primal dual algorithms in general, is that when we terminate with our feasible primal solution, we know that because we're using the complementary slackness conditions, that this feasible primal solution is actually the optimal solution. We saw this in our optimality criterion in the previous lecture, but we'll mention it again coming up. The key algorithmic components of the primal dual algorithm are a primal update step and a dual update step. We can imagine that we start with some initial dual solution, and so the first thing we do is a primal update step. In the primal update step, we use complementary slackness to form the set of edges. That is, every time we see a tight constraint, or rather our updated weight is equal to 0, we use that edge as part of our primal solution. The way we use that edge, this set of edges, is by finding a maximum matching among these set of edges. After we find a maximum matching with, say, the label scan algorithm, we'll also output the set of labeled nodes in V1 and V2. If it happens that in our primal update step, the number of edges in our matching is equal to n, then we terminate. Otherwise, we move to the dual update step. In the dual update step, we look at the nodes that are labeled and form a set of edges that we call E bar. E bar is formed by all edges that have one end in V1+, that is, it's a labeled node of V1, and the other end is an unlabeled node of V2. Across all these edges, we look at all of the updated edge weights and find the smallest one, or the smallest negative one. We call this quantity delta, and we update our dual values with this delta. Specifically, for any labeled node in V1, we update the weight of that node by subtracting delta. For any node that's labeled in V2, we update the weight of this node by adding delta. We'll see the reason for this particular value of delta and this particular dual update in just a little bit, but a broad overview is that we're picking a value delta, the smallest such one, so that we retain a dual feasible solution, and we're updating it in such a way that our dual solution improves in objective value. The way we use this primal update and this dual update is in an iterative way. We start with some dual solution. From this dual solution, we do the primal update step, And if we don't terminate, we come to the dual update step. After we do a dual update step, we return to the primal update step. By doing the dual update, there's going to be more constraints that are tight, and so the set of edges E is going to grow in size, and so our matching should grow in size. At some point, we're going to break out of the cycle at the termination condition. That is, we're going to find some point where the number of edges in our matching in the primal update is equal to n. At that point, we stop the cycle and we terminate the algorithm. Ultimately, we'd like to show that when our algorithm terminates, that the linear program solution is equal to the dual solution, the two solutions that we've constructed, and therefore the solution that we are going to output is optimal. Before we get to that, though, we're going to need a few claims. The first claim is that when we have a matching M in our primal update step, after we do a dual update step, this matching M remains a matching. To show this, all we need to show is that all of the matching edges are still associated with tight constraints. This is easy to see. If we have some matching edge, M, then we saw in the label scan algorithm that either both of the endpoints are labeled or both of the endpoints are unlabeled. In either case, the updated weights are unchanged, and so the constraint remains tight. The second claim is that our labels at the end of our label scan algorithm are going to remain valid labels after we do the dual update. To see this, all we need to show is that the updated weights for all the edges that go across labeled nodes stay the same. If this is the case, then the label scan algorithm can continue just like it did before. There's no edges that are removed. Edges are only added. Because this is true, we can sort of continue the label scan algorithm at exactly where we stopped. These two claims together tell us that the matching and labels returned at the end of our primal update step can sort of be put into the next primal update step, and so we can continue. The second set of claims is related to the dual. The first claim is that the dual objective value decreases. It gets better. That's because the dual is a minimization problem. This happens because of a property of the label scan algorithm that we observed in a previous lecture. Specifically, the number of labeled nodes in V1 is greater than the number of labeled nodes in V2. Since we decrease every node in V1 plus and increase every node in V2 plus, the number of decreases is greater than the number of increases, and so overall the dual objective decreases. The final claim we'd like to show is that after a dual update, the dual variables are feasible. In this case, remember that feasibility means that our updated weights are all going to be less than or equal to 0. To see this, we can note that there's only one type of edge where the updated weight is going to be increased. This edge has one endpoint in V1 plus and the other endpoint in V2 minus. But we chose our dual update rule so that exactly these edges are taken into account, and we won't increase the weight of these edges by any more than delta. Delta is chosen in such a way so that all the constraints remain satisfied. Together, these two claims tell us that the dual gets better. The dual remains feasible, and the dual objective decreases. In this way, our dual update step is making a better dual solution. Now we can see why this solution is going to give us an optimal solution at termination. This comes from the optimality criteria that we mentioned in the last lecture. This optimality criteria tells us that if we have some dual solution and some primal solution, so that our dual solution is dual feasible and complementary slackness holds, then X is an optimal primal solution and U and V are an optimal dual solution, and the objective value of both is equal to the sum of the weights on all of the edges, on all of the nodes rather. The way we can view the primal dual algorithm is that at all times we have a dual feasible solution, but at no time until the very end do we have a feasible primal solution. A feasible primal solution matches every node in V1 with a node in V2. Only at the end, when the size of our matching is equal to n, do we have a feasible primal solution X. At this point, we have an X, a U, and a V that satisfy our optimality criteria. And so, at the termination of our algorithm, we have a feasible primal solution And automatically, because we're in the primal dual framework, we have an optimal primal solution. The final thing we'd like to show is that our algorithm does in fact terminate. To show this, we need to note two things. First, after every dual update, v2 plus is going to increase. That is, the number of labeled nodes in v2 is going to increase. This happens because, as we showed, the old labeling is feasible, so we can start with it. And we've added some new edge, ij, from e bar, the e bar found in our dual update step. With this new edge, we're going to have at least one new label in v2 plus. That's because this edge, e bar, goes from some labeled node in v1 to some unlabeled node in v2, and our label scan algorithm is now going to label j. This claim implies that our matching m has to increase in size after n updates. This is because the number of labeled nodes in v2 is at most n, so it can increase at most n times. So after n times, something else has to happen, and that something else is that we find an augmenting path and update our matching m. This shows that at some point our primal dual algorithm is going to terminate, and we know now that when it terminates we have a feasible primal solution, and because we're in the primal dual framework, we automatically know that this feasible primal solution is an optimal primal solution.